So in the previous lectures, we have seen that given a basis, it gives you a topology on that set. Now we can ask the question. The question is that given a topology, so if you start from a basis, you get a topology, but given a topology tau on a set X, is there a basis? Is there a basis B on X that generates tau? Okay, so we have this arrow from basis to topology, but if you start from a topology, whether we can go back and get a basis which then generates a topology. Okay, so we complete this circle of arrows. So to answer this question, let me start with a lemma. Lemma is that if B is a basis that generates a topology tau, then any open set U, so U is in tau, can be expressed as an arbitrary union of basis elements. So tau, the topology tau has open sets which can be expressed as an arbitrary union of basis elements. Of course, arbitrary union of basis elements are themselves open, so tau consists exactly of arbitrary unions of basis elements. In fact, tau consists exactly the arbitrary unions consists of exactly the arbitrary unions of basis elements. So let us see a proof. So the first part, so let me first note that if B alpha is a collection of basis elements in B, then this union, arbitrary union of these B alphas, belongs to the topology generated by B, since each B alpha belongs to the topology itself. So each B alpha is an open set. So B alpha is in tau for each alpha in J, and we know that arbitrary unions of open sets are open. So this is okay. So it is now we only have to show that given any open set, it can be expressed as an arbitrary union of basis elements. So suppose that U is in tau, then for each X in U, there exists a basis element which I denote by Bx in B, such that X belongs to Bx and it is contained inside U. Then it is easy to show that U is exactly the union of all these Bx's where X is in U. So here I am taking the index set as U, index set J as U itself, and taking the union of all these basis elements. So why is this true? So first of all, since Bx is a subset of U for each x, so then x in U Bx is a subset of U, since as Bx is in U for each x, and also to show the reverse inequality, so let y be in U, then by is contained inside U and it contains y. So this is how we chose it, and this means that y belongs to this union of basis elements Bx. So when you have a y, the set By is one of the sets in this collection, so y belongs to this union. So this means that U is equal to basis. So here we see a theorem which answers our question on how to get a basis for a given topology. So the statement is that starting with a topology tau on a subset X, we define for each ordered pair X comma U. So here U is an open set and X belongs to this open set. So we take all such ordered pairs where the first coordinate is a point in an open set, which is the second coordinate. So we define for each such pair this collection CXU, which is the collection of all open sets such that these open sets contain X and they are contained inside U. So this is a collection of open sets. And now if B is a collection of open sets again in X, such that the intersection of B with CXU is non-empty for any XU, any pair XU, then I claim that B is a basis for this topology. So let's see a proof on why this theorem is true. So there are two parts to this, to proving this theorem. First is that a B is a basis, and second is that the topology generated by B is the topology tau that you started off with. So let's start with proving that B is a basis. So to show that B is a basis, we have to check these two properties in the definition of a basis. So the property 1, to prove property 1, let's take an element, a point X in X, and we have to find a basis element which contains this point X. But we note that since X itself is an open set, then B intersects the collection C X comma X. Okay, so this is the collection of all open sets which contain X, this point X, and this is non-empty by our hypothesis, by the property of B. So this means that there exists a basis element to B in B such that X belongs to B and it is contained in X, and this is what we want for the first property. To prove the second property, we let B1 and B2 be basis elements and take X in the intersection of these two basis elements, and we have to produce, to show that there exists a B3 such that X belongs to B3 and it is a subset of B1 intersection B2. So notice that B1 and B2 are open because if you go back to the statement, B is a collection of open sets. Okay, so all members of B are open. So in particular B1 and B2 are open, and this means that B intersects the collection C with X in the first coordinate and B1 intersection B2 in the second coordinate, and this intersection is non-empty. Okay, so this means that there exists a basis element B3 in B such that X belongs to B3 and it is a subset of B1 intersection B2. So we have proved that B is a basis by verifying the two properties needed for our definition of the basis. Now the second part is that the topology generated by B is exactly tau. So suppose that the topology generated by B, this collection B, is denoted tau prime. So we have to show that tau is equal to tau prime, and for this we can show that tau is included in tau prime first of all. So let U be an open set in tau, and so we have to show that U is in tau prime. So because U is in tau, for any X in U, we have B intersection CXU is non-empty. This means that there exists a basis element B, B prime, let's say, in tau prime, in B, such that X is contained inside B prime and it is contained inside U. But this means that U is open in tau prime. Okay, this is the definition of an open set in terms of the basis elements. Okay, so we have shown that tau is included in tau prime. Now to show the reverse part, tau prime is included in tau. Take any open set U prime inside tau prime. Now from Lemma 6.1 above, we have that U prime is a union of basis elements B prime. So U prime is a union of basis elements in B, but each B prime is open, is an element of tau, because B was a collection of open sets. So this means that U prime is an arbitrary union of open sets, and therefore it is open in tau. So this means that tau prime is included in tau, and so tau equals tau prime. So we have shown how to first we have shown a way to define a topology from a basis, and in this lecture we have defined we have given a way, given a topology, how to find a basis that generates the same topology. And let me end with another definition, and it is of a subbasis. So what is a subbasis? So a subbasis on a set X is a collection of subsets of X whose union is X. So we had this basis that gives you a topology, and the notion of a subbasis is something below the basis, meaning that a subbasis gives you a basis which can then give you a topology. So how does one go from a subbasis to a basis? So here's a small lemma, which is that if S is a subbasis on X, the collection B, defined as the sets U, subsets of X, U, such that U can be expressed as finite unions, finite intersections of elements in S. Okay, so these are B is the collection. B is the collection of finite intersections of elements in S, and then this B is a basis. So given a subbasis, we can define a basis in this way. So let us check the conditions for B being a basis. So property 1, so given X in X, since we have that X is the union of all sets in S in this subbasis, this means that X belongs to S for some subbasis set S, and this means that if you take B to be S, then of course S is a finite intersection of itself, so it belongs to this basis element and it contains X. So the first property is satisfied, and for the second property, so let B1 and B2 be elements of B and X be in B1 intersection B2, and we have to show that there exists a B3 in B which contains X and it is contained inside B1 intersection B2, but I claim that this itself is can be taken as the set B3. So how does this work? So if B1 equals S1 intersection S2 intersection Sn, so it's a finite intersection of subbasis elements Si in S, and B2 is S1 prime intersection S2 prime Sm prime Sj belong to Sj prime belongs to the subbasis. Then of course B1 intersection B2 is S1 intersection Sn, and then intersection S1 prime Sm prime, and this is a basis element already because it is a finite intersection of subbasis sets. So this means that you can just take B3 to be B1 intersection B2 itself and it contains X. So property 2 is satisfied, and therefore this is a basis. B is a basis. So we have seen now that to define a topology, we can either first of all give it an explicit description in terms of open sets. The second way is to define a basis, and the third way is to define a subbasis, and all these three ways can give you a topology on a set X. So in the next lectures we will see various different kinds of topologies, and we will see examples of those as well.